In just a few short years, artificial intelligence has gone from science fiction to everyday reality. It writes text, makes art, drives cars, even helps discover new drugs. But all of this incredible progress comes with a price. It demands a massive amount of computing power, and that demand is growing faster than ever before. The problem? Our current computer chips are starting to max out. For decades, we've ridden the wave of Moore's Law, a kind of unofficial rule that says the number of transistors on a chip doubles roughly every 2 years. In simple terms, it meant that computers got faster, smaller, and cheaper, like clockwork. Your phone today is more powerful than a room-sized supercomputer from the past. But Moore's Law is slowing down. As we try to cram more and more transistors into tiny spaces, we're hitting the limits of physics. Chips are running hotter, drawing more power, and getting harder to shrink. At some point, you just can't make transistors smaller without running into serious problems. So now the tech world is asking a critical question. What comes after Moore's Law? Some experimental ideas are in the works, like chips made from graphene, computers that work on probabilities instead of exact answers, and quantum machines that manipulate atoms. They're fascinating, but most are still in the research phase. Meanwhile, there's one surprisingly practical solution that's already working today, and it doesn't rely on electricity the way traditional chips do. Instead, it uses light. These are called photonic computers, and they could be the key to unlocking the next era of ultra-fast, energy-efficient computing. Let's dive into how they work and why they might change everything. In a standard processor, like the ones in your phone, or in a powerful GPU, everything runs on electricity. Data is represented as streams of ones and zeros, and these are controlled by moving electrons around tiny circuits. The electrons travel through copper wires, and it all happens incredibly fast. Billions of operations every second. Now, here's something that might surprise you. The issue isn't how fast electrons can move. In fact, they're fast enough for most computing tasks. The real bottleneck comes from what needs to happen around those electrons to actually process information. Every time a chip switches from a 0 to a 1, or the other way around, it has to charge or discharge a tiny electrical component called a capacitor. Think of a capacitor like a miniature bucket that holds charge. Every time you flip a bit, you either fill it or empty it. That might not sound like a big deal, but when you're doing this billions of times every second, those little pauses add up. It's kind of like trying to sprint across a city, but having to stop at every single traffic light. Sure, you're fast, but the stop and go slows everything down. Now, this is where light changes the game. With photonic chips, we don't need to play the start-stop game. Data travels as light waves, photons, and instead of stopping to charge and discharge components, the information just flows constantly. Imagine sending a car down a highway where all the traffic lights are green forever. That's what photonic chips do. Even better, calculations can happen while the data is still moving. This is called in-flight computing. You're processing the information without needing to pause it, and the speed is off the charts. These operations happen at the femtosecond level. That's 1/4,000,000th of a second. To put that into perspective, light could circle the Earth almost 8 times in just 1 second. That's the kind of speed we're talking about. But speed is only half the story. One of the most fascinating advantages of using light is that it naturally allows for analog computing. Let me explain what that means. Traditional chips are digital. They think in ones and zeros, binary. Everything, no matter how complex, has to be broken down into a long sequence of binary steps. Whether it's doing simple math or transforming a photo, it all boils down to flipping billions of transistors back and forth between on and off. But light isn't limited to binary. It behaves in a smooth, continuous way. It has amplitude, frequency, phase, and all of these properties can be used to represent and manipulate information more directly. That's the key difference. With light, we can perform certain types of math natively, in one go, instead of step by step in digital form. Let's take some examples. Say you want to add 2 numbers. A digital chip needs around 200 transistors to do that. Now try calculating a square root. Suddenly you need 7,000 transistors. Want to do a Fourier transform, a complex operation that's essential in audio, image, and signal processing? You're looking at over 1,000,000 transistors. Now here's where it gets mind-blowing. That same Fourier transform can be done using just one optical component. No power consumption, no heat. Just light flowing through the right kind of lens or waveguide. If you wear glasses or use a camera lens, you're already benefiting from this principle. Lenses physically transform light as it passes through them. In fact, lenses do a type of Fourier transform every time they focus an image, and they do it passively. way, without using any electricity. Photonic chips take that idea and scale it into a full computing system. These chips use optical devices like beam splitters, waveguides, and modulators to manipulate light as it travels through the chip. They're designed to perform math operations directly on the light signals with almost no energy loss. Here's the kicker: because these parts are passive, meaning they don't need electricity to operate. They don't generate heat the way traditional chips do. That's a huge deal. Heat is one of the biggest challenges in high-performance computing. It limits speed, drains power, and forces us to use elaborate cooling systems. With light-based chips, you can perform complex math using a fraction of the energy in space. You're replacing thousands or even millions of transistors with a single optical part, and you're doing it without needing cooling fans, heat sinks, or massive power supplies. And this isn't just theoretical anymore. A company called QANT, based in Germany, has built a commercial photonic computer chip. They call it the NPU, short for Native Processing Unit, and it's exactly what it sounds like: a processor that computes natively using light. The chip doesn't rely on electricity to move data through circuits. Instead, photons carry the information, and the chip uses specially designed photonic structures to process that data in real time. And this isn't some lab prototype, it's already out in the wild. The first versions of QANT's photonic chips are being shipped to high-performance computing centers, where they're being tested in real-world applications. We're not talking about 10 years in the future. This is happening right now.
Our first application will be satellite control. This will enable direct optical communication between satellites in orbit.
What makes QANT's chip special is the material it's built on.
At Quant, we have found the optimal material combination that enables the integration of low-loss photonic components together with its control electronics onto a single chip.
Lithium neobae. It's not your average chip material. This crystal lets them guide and control light right on the chip without bouncing it between different layers. That's important because light loses strength every time it crosses into a new material, so keeping it all in one reduces signal loss and keeps things accurate. Even cooler, lithium neobae can steer light just by applying voltage with no current needed. That means no heat, which means faster, cleaner signals. Thanks to that, QANT has managed to reach 8-bit precision, a major achievement for analog photonic chips. Another thing that sets QANT apart: they're doing everything themselves. Design, manufacturing, software, you name it. Most startups don't do this, but photonic chips need a totally different production method than digital ones. Light circuits are physically larger, so the tiny high-end factories used for traditional chips aren't actually necessary here. In fact, QANT can use simpler, even recycled factories, which could be a big win for scaling and sustainability. If you enjoy getting updates about microchips, hit the subscribe button. See you in the next video.